Hi, this is Dr. Simon Romero. I'm here to present you the video tutorial for finding absolute maximum and absolute minimum values of a function of two variables. First of all, I'm going to talk about boundary points. So a point AB is in the boundary of a set A if every disk centered at AB contains points in A and points not in A. The boundary of A is the set of all boundary points. So, this is a complicated definition of a very simple concept. So in this case, this point over here, I'm just pointing right now, is in the boundary because it doesn't matter what disk you take. It always has points in A and points outside of A. The other two points that I have right here are not in the boundary because they have disks that have only points in A or points out of A. So that's the idea of boundary points. And now I'm going to talk about closed and bounded sets. Domain A is bounded if it is contained in a disk, and domain A is closed if it contains all its boundary points. So for example, in this case, all these two are bounded, but this one is closed because all the points are included in the domain, and the other one is not going to be closed because it doesn't include some of the points in the boundary. So now we're going to talk about how to find absolute max and absolute min values. The idea is going to be very similar to the one that we saw in functions of one variables. So the idea, first of all, we're going to use something called the string value theorem. We're going to say a function is continuous in a closed and bounded domain in R2, then f attains its absolute maximum value and its absolute minimum value. So if you want to guarantee a continuous function to have an absolute maximum and an absolute minimum values, you just have to define your function in a closed and bounded domain. So, to find those values, by the way, if you are interested in this theorem, you have to take a class that math majors take that is called real variables 2. So let me just return to this if you're not really not interested in the kind of the reason why this is the way it is, and don't worry about what I said. Don't worry taking that class. But anyway, so we have that. How do you find these absolute max and absolute minimum values on a function defined in a closed and bounded domain? And the idea is very simple. You have to find the critical points. Now notice that we are not going to use please don't use, in these kind of cases, no second derivative. I forgot to put it in the presentation, but you don't need to use the second derivatives test here because the second derivatives test is just going to tell you if you have a local max or a local min. That in this case is not actually very useful. So you're going to find the critical points of A, and then you're going to evaluate also in the boundary. The only possible cases that you can have an absolute max and an absolute min is in the critical points or where the function is cut off, or where the graph of the function is cut off, and that's going to be in the boundary. So you find the largest of the critical points, you have the largest of the points in the boundary, and the largest value is going to be the absolute max, and if you do for the smallest value, you're going to have an absolute min. Let me give you a particular example. So let's try to find the absolute maximum and the absolute minimum of this function on the closed rectangular region described by these two inequalities. So the first thing that I want you to notice is that our domain is actually closed and bounded. Are all the points such that the x-coordinate is between 0 and 3 and the y-coordinate is between 0 and 5. So now we're going to follow the steps. The first one is find the critical points of f in A. In order to do that, we set our partial derivative is equal to 0, and then we start solving the equation. And the thing that we have is from 1 we obtain that y is equal to x cubed, and then plugging into 2 you obtain this thing over here. So either is x is equal to 0, x is equal to 1, or x is equal to minus 1. If x is equal to 0, we have that y is equal to 0 because y is equal to x to the cube. If x is equal to 1, then y is equal to 1 again because y is equal to x cubed. Since we're worrying about the x's that are between 0 and 3, we don't consider the case when x is equal to minus 1. So the critical points that are in our region are 0, 0 and 1, 1. Now we're going to take the values of the function at those points. So we have that f of 0, 0 is equal to 2 when we plug in, and f1 of 1, 1 is equal to 0. So now we are done with step 1, that is finding the outputs, or in other words, the values of the function at our critical points. Now we're going to worry about the boundary. For the boundary, the thing that we're going to do is notice that our boundary consists of 4 line segments here, and we're going to divide it. We're going to treat each segment individually. So let me just start with this segment, y equal to 0 and the x goes from 0 to 3. So if y is equal to 0, we can plug in the formula for the function y equal to 0, and that is going to give us a function of one variable. Notice that by doing this, we reduce our problem to find the absolute extreme of functions of one variable. And we're going to use what we did in functions of one variables. We use the closed interval method that's so in single variable calculus. So the thing that we have to do is find the critical numbers of the function of one variables, and then evaluating also at the endpoints and taking the largest and the smallest. And we're going to do the same thing here. So we're going to find the critical points. The critical points is when x is equal to 0. Then we're going to evaluate at the endpoints and the critical points. So the critical point and the endpoints are actually the same. Notice that that's 0 is the critical point of G1, and these are the endpoints of this particular line segment. So the thing that we have is the value at 0 is equal to 2. That at the original function will give you f of 0, 0, and the value of the other endpoint, that is when x is equal to 3, and that will give you the point 0, 3, and the value of that of the function is 83. So we have now finally done these two. So we're going to repeat the process for the other 3 line segments on the boundary. So let's start with the next one. Now we're going to do x equal to 0, and we're going to repeat the process. We're going to plug in x equal to 0 into the function, gives you this function over here. We find the critical points for g. In other words, we have to take the derivative, set it equal to 0. We found that y is equal to 0. We have the endpoints and the critical point, and we evaluate at the endpoints and at the critical points. At the critical point happens to be also the endpoint, so you end up with 0, 0, that we already knew what was the value anyways. And the other one is going to be 0, 5, that is when y is equal to 5, and that's the other endpoint, and that gives you 627. So now we have these 4 values, and we will continue in our boundary. So now let's take the next line segment, that is this one on the top. So we're going to have y equal to 0, and x is going to move from 0 to 3. So if you plug in y equal to 0, you obtain this function. We find the critical points of G3, we take the derivative, solve for x, and the thing that we will end up is 5 to the 1/3. So the cube root of 5. Since x is between 0 and 3, we evaluate at the endpoints that are 0 and 3, and the critical point that happens to be 5, the cube root of 5. The cube root of 5 certainly falls between 0 and 3, so we have to evaluate. So we start at 0. At 0, we have that x is equal to 0, y is equal to 5, so we end up with 627. At the critical point, we're going to have 627 minus 3 times this expression right here, and that's going to be f of that. I don't need to compute this because this is certainly less than 627, so, and it's bigger than other things that we have computed, so this is not going to be a relevant number for us. And the last one is 3, that it happens to be the other endpoint, and that's going to give you 648, and that is going to give you this corner right here. And so far this is the biggest one that we have found. Finally, we're going to do the last boundary, and it's going to be the line x equal to 3, the line segment x equal to 3 when y goes from 0 to 5. So we have x equal to 3, we end up with this function. We find the critical points by taking the derivative, set it equal to 0, and that gives you this particular critical point. So we have to evaluate at the critical point and at the endpoints. So at the endpoint 0, we obtain f of 3, 0, that is 83. Again, we already compute that one before. G4 at the particular critical point, and it's going to give you 83 minus a number here, and notice that that's less than 83, so it really does not going to play a role in deciding which one is the largest and the smallest one. And the last one is the endpoint 5, y equal to 5, and that gives you 648, and that one we already computed before. Notice that, I mean, if you're in a celebration of learning, you do have to do all this process because you really don't know which sometimes the absolute max and the absolute mean is not going to be in the corners. It's a common mistake thinking that the corners are the only thing that you need to evaluate, and that's not the case. You have to evaluate the critical points of the function f and the critical points of each of the individual functions in the boundary. So the largest value from the previous two steps is going to be the absolute maximum value, and the smallest one is going to be the absolute minimum value. So now we just have to find what is the absolute maximum, or what is the largest value, and in this case the largest value is 648. Notice that anything else is less, and the smallest one is going to be 0. So the thing that we can conclude is 648 is the absolute maximum value and 0 is the absolute minimum value. And with this we finish this video tutorial for maximizing and minimizing functions in closed unbounded domains. Thank you.